It's always great to be the last speaker. But anyhow, this talk is going to take about less power or less energy than one of those Google thingies in 1 picosecond. So think about it. So we've been talking a lot about power and obviously about Moore's law and things like that. But one of the key things about Moore's law is one of the consequences is that not only get more transistors, but also is that things are getting smaller. Miniaturizing. And basically, suddenly things that we can actually start packing more and more functionality in smaller volume over time. And suddenly, it might enable things that were impossible before. And that's really what this is all about. It's really about miniaturization, and related to that, the idea of ultra-low power dissipation. So let's talk about human enhancement. So if you start thinking about electronics that start to come of the size of electronic components or systems, that become of the size of, let's say, less than a cubic millimeter. Let's say maybe a couple hundred microns on the side. Suddenly you can start doing amazing things. If I start putting enough functionality in there, I can start thinking about electronic nodes that are so small that they actually start becoming the size of a biological cell, or around that size factor. And we start being able to do interesting things like observing living cells in vivo while they're in the body and discover certain properties, do diagnostics, maybe do some stimulation or do some drug delivery or something like that, or create some new interfaces to those cells, actually start talking to those cells in real time. This has gotten the name that somebody invented this name, which is called nanomorphic biointerfaces. And I don't know what it really means, so you go to Wikipedia. Wikipedia tells you that this is something about a self-sustaining micro system which has a number of functionalities integrated to it. Obviously sensing. It has to have somewhere an energy supply. That's very important. It performs actuation potentially, and there's computation and communication. So what we're going to do in this talk is kind of look a little bit at where we are in this space and what are the kind of key challenges we have to resolve to really get there. And the interesting part is we've gotten a lot closer than I really expected a bunch of years ago. So I'm going to actually focus on one particular area here, which is the area of brain-machine interfaces. And that's what really going to be talked about. So why brain-machine interfaces? So neuroscience, for a long time, a lot of the developments in the earlier neuroscience were based on static analysis. You take a dead brain and you slice it apart and you figure out how the neurons are connected. But then with better and better instrumentation, we start being able to observe brains while they're in action. And the first things obviously are these big machines like fMRIs, allows you to do some analysis. But that's also still limited because it's not a real human basically in action because this is a big machine. So what you would like to see is imaging strategies that allow you to look at brain activity while you're moving around in your daily life. And not only that, basically start using that imaging to do certain functions. Functions like, for instance, addressing neural impairments. People who had certain illnesses. So a lot of people have strokes, have spinal cord injuries. There's a variety of things. So people have come up with a set of approaches to address those, like cochlear implants, very popular today. Artificial retina has been worked on for quite a while, but still not there yet, but is getting to a certain point. Deep brain stimulation, very effective today in addressing Parkinson's disease. And neuroprosthesis. The neuroprosthesis idea of linking directly to neurons and for people who had stroke, spinal cord injury, and making them move some limbs again. And potentially, then you start thinking about, once I have that interface to the brain, to the neurons, I might be able to do other things as well. And this is the whole area of human enhancement. We're not there yet by any means, but you can actually have your fantasy running wild when you start thinking about this. But the bottom line is this enabling of this type of approaches really creates a new decade of neuroscience. And potentially it might have a huge impact. Not only on neuroscience itself or neurosurgery itself, but also as other things like neuro-inspired computing. It might help us rethink a little bit how to do some computational functions. So the area I'm going to talk about is BMI for motor control. So the idea here is that people who've had spinal cord injury, you have a 17-year, 18-year-old kid driving a car, hit a tree, bingo, that's what you get. Basically, the spinal cord gets snapped right there. All communication between the brain and the limbs is cut off. So the brain is still perfectly fine, but the links, the communication has disappeared. It's a big problem. It's, if you look at it, there's 11,000 new cases in the US every year. So what can you do about it? Well, maybe what I could do is have a set of interfaces that you put on the motor cortex, the area that basically drives motor functions, and measure signals that are happening there, bring those signals externally to and feed it to some control algorithms that then in turn basically manage or basically control a prosthetic device like a robotic arm. Now obviously you have to realize that this whole thing is always going to be a feedback system. That's the only reason it works. If you would just have this in open loop, it will never fly. But what you have is feedback, which could be visual. You see where that arm ends up. Or you have tactile feedback. You feed it back into the brain, and this closed loop basically converges quite rapidly. And that's why it works, because of the fact that brain is such a plastic environment. So a bunch of groups are working on this. For instance, this is work, a lot of it is driven by the group at Duke, Nicolelis group over there. Now, the question is, how do you measure those neural activities? How do you basically image those things in deep? So there's a number of ways of doing imaging of the brain, different strategies. The first one, very well known, is electroencephalography, where you put a bunch of electrodes on top of the skull, and you measure a certain set of waveforms that you can observe. Typically, those waveforms give you frequency contents between 0 to 50 hertz. They're very noisy signals, so SNR is so low that you get very little information above 50 hertz. So what you really see is alpha beta waves, which are the results of many, many neurons firing in phase synchronicity. And they create these low frequency waveforms. Interesting, you can do some stuff with it. You can observe those signals, and actually you can use this to control certain things. Like, for instance, this is an example of a person driving a wheelchair and making it stop and go left and right by just observing basically EEG signals. But you can imagine with about 3 centimeter spacing between the electrodes, you basically have millions of neurons per electrode, which means that the overall resolution I'm going to get is limited. Number of actions maximally that you can kind of take apart is about 5 to 8 for really good people. So the real opportunity for brain-machine interface is really to go deeper. If you really want to have real signals, high-quality signals, you have to go below the skull. And the first step to do so is something which is called Econ, or electrocorticography, where you put a membrane with electrodes on top of the dura. On the top of the dura, it's a bunch of electrodes which are about half a centimeter apart. You can see it right here. This is an open skull surgery. And the fact that you're now so much closer to the cortex, you're really almost on top of the cortex, you get much better signals. So your SNR has improved substantially, and now I get signals that go to about 300 hertz approximately. Still low frequency waveforms, still hundreds of thousands of neurons per electrode. But a lot more interesting, and you can start doing interesting things like this. You can actually start doing mapping of functionality onto different regions of the brain while things are happening. However, still limited in its amount of resolution. If you really want to move an arm with 20 degrees of freedom, you have to almost go to the single neuron. You have to have electrodes that are sitting next to individual neurons and measure the waveforms basically of the neurons firing. And the way this is done is by having electrodes that poke about 1 millimeter to 2 millimeters into the cortex and basically observe the voltage waveforms that are generated by individual neurons. And people have demonstrated this can be done. You've seen probably some of those movies where monkeys are sitting in a chair and just by brain power move an arm, grab marshmallows, or move a computer pointer without ever moving an arm whatsoever. So the key thing is you really want to do high resolution BMI, you have to be in this particular space. So that's what I'm going to focus on initially, and then I'm going to backtrack a little bit later in my talk. So this is really what you want to build. You have a set of electrodes, and there's a bunch of companies today coming out of universities, Utah, Michigan, have all made electrode arrays, which have a bunch of electrodes out there that you can put in the cortex, and then you can make an interface that connects to the outside world. But really, this is the node that you have to think about. Electrodes, you have to acquire those signals, which again are very noisy. You have to amplify them, A to D convert it, maybe do some signal processing on it, because otherwise you have to send so much information outside. And then basically connect this wirelessly to the outside world. You don't want to have a wire pocket to your skull. It's not very healthy. It basically has all kind of risks that come with it. So having a wireless interface to those nodes would really be nice. Then you have an external node providing maybe power. So somewhere you have to have a power source for these things. There have to be clocks, all those kind of things. Now that's all nice, but the real problem is that this thing is going to be extremely power limited. Because you want to make them small. Small is good. Actually, this is kind of the waveforms that you're trying to acquire. This is a typical waveform, not a typical waveform, this is a very good waveform that you might see from one of those systems. This is actually measured from a rat. And you can see here, this is the waveform that you observe when you put the electrode next to a neuron. You see a couple of factors. Number one, there's a huge DC offset. There's an offset of about 50 to 100 millivolts. There's a lot of noise, very noisy signal. Occasionally you can see some spikes. These are neurons firing, and they have about amplitudes of about 10 microvolt to about 1 millivolt. And then on top of that you have this low frequency waveform, which is indeed again what you see with Econ or EEG, is the combined factor of all the neighboring neurons firing in synchronicity, phase synchronization between neurons. So what you would like to do is really, I'm interested in this. I would like to get those spikes out of there, figure out the timing, and send the timing to the outside world. And I'd use that basically to control my functionality. But the problem is it's weak signal, low SNR, high offset, and you have a mixture of data there. And you have to be able to build those things such a way that they last for 10 years. Because if you do an implant in the brain, you don't want to go back every couple of months. You want to keep it there for 10 years. That's kind of the timeline that people want to shoot at. So another thing that is, you want to do all those things and you want to make it in a small form factor. What's small form factor? Well, obviously, you want to observe very small things. You want to get close to a neuron. You have to be very small. That's one thing. So resolution observations are really at the neural level. This is an example of the cortex. These are the 5 layers of the cortex. This is one of those electrodes poking through. So in this case, this picture here, you see 3 different neurons, spaced about a couple hundred microns apart. So we really need to have a resolution of about 100 microns. That's one thing. The other thing is that if you make the nodes too big, some bad things happen. You put something, a needle in there, your brain is not a very static entity. Every time you shake your head, it kind of goes back and forth a little bit. It's a very plastic type of environment. So what's happening is that in rats, you put electrodes in, you get beautiful signals for a couple of days, and then it starts to go downhill and the sensitivity disappears. With monkeys, maybe a year. That's the max people say. After a year, you start seeing the downhill type thing. And one of the main reasons is indeed this scarring that basically starts forming around the electrodes. You move the head, it basically gets some damage. This micromotion basically creates some impact. So the real way to avoid that is if your electrodes would move with your brain, you might have less damage, you might have less impact on the overall thing. So we need to think about free-floating electrodes that are sitting in the cortex and can minimize the amount of damage you will see. But that basically requires really tiny components. And with tiny comes low power. Right? It's all about power. Actually, it turns out anytime I do electronics, the more volume I have, the more electronics, the more energy I basically can consume. If I make things very small, you only have a very tiny amount of power available and energy available. Now, how to get power into those nodes? Well, I can use batteries, but that's not very attractive. I put battery materials inside the brain, and you have to replace them occasionally. Not a good idea. So energy scavenging looked like the perfect thing to do. But it turns out there's only a limited amount of energy that we currently know how to harvest. You can think about heat. Okay, so I have some gradients. But again, you don't want to have that many temperature gradients in the body. Or you have to put a thermal element on the outside and the inside, means a cable. And still the power you can get is very limited. One thing you can think about is maybe biofuel cells. That's attractive. Right? It's the same thing as your body does. You take sugars, glucose, you put oxygen with it, and suddenly you generate electricity and some gluconic acid. Interesting idea. Will go somewhere, I think, but today we're getting about 0.7 microwatt per square millimeter. So that's the numbers you have to start thinking about, microwatts, not these megawatts of the Google guys. So this is not working. So the only thing that really is viable today is outside powering. It's our kind of artificial energy harvesting. You put a power source outside, and you transmit power to the node using electromagnetic or magnetic or electrostatic waveforms. That's kind of the idea. The advantage is that the power source is outside the body, but there's some limitations. Because now I'm starting to expose the body to electromagnetic waveforms, and people are kind of worried about that. So the key question is how much can you get, right? How much can you get by doing electromagnetic waveforms, and you look at nodes that are about a cubic millimeter in size? That's kind of the thing you would think about. Well, there's 2 concerning factors. One thing is that this is not a very good transmission channel. You have an antenna outside, and it has to go to skull, bone, fat, hair. that basically is not as good as air in terms of transmission. So you have a loss factor which is larger than you would get with pure transmission to air. The other thing I already mentioned is that the regulatory bodies are putting maximum values on the amount of electromagnetic power or electrostatic power, or magnetic power I can basically expose the brain to. It all boils down to 1 degree Celsius. That's the standard. You can never make a temperature in a certain area go up by more than 1 degree Celsius, and that basically determines the maximum fields you basically can apply to the body. So you bring all those things together, and there's also, obviously, there's the self-heating. If I put a very high-powered device into the brain, it starts generating energy, it starts heating, because it might be more important than basically the power of the transmission itself. But the bottom line is, if you plot the amount of power I can get, using optimization, you look at the optimum frequency, optimum antenna size, and all those kind of things, you can see that if I get about a centimeter-sized antenna inside the brain, I can get about maybe tens of milliwatts. But then you start going to smaller and smaller sizes, and that's where the real problem is. Your amount of energy you're getting is going down as more than d to the 4th in terms of the size of the antenna. So the smaller the antenna, the larger the energy loss. So at around 1 millimeter, I get maybe 10 to 20 microwatt. That's the number of power I can basically get. So that's what we have to live with. That's what we have to design. Can I design all the electronics I need to for that particular power budget? Power determines functionality in this particular case. So how to get around that? Well, here's kind of my rules of how to design those things, the rules of ultra-low power design that basically apply to this space. And number one is efficiency. Obviously, you cannot afford to waste anything. So every electron counts. Optimizing everything to the extreme is extremely important. Number two might not be obvious. Actually, a lot of people in the medical industry think that you're better off with older technology nodes. Actually, I believe the opposite. Actually, by scaling technology, I can still get major advantages in power reduction. And actually going and embracing technology scaling is a good thing to do. Pushing as hard as you can on the supply voltages is the other one. And I'll show you some examples of how you want to push those things down, way beyond what you typically will do. And then rethink computational and communication paradigms. Think out of the box. Rethink way to do functionality. That's why I see all those new devices that I've heard about yesterday. Hey, if one of those things pops up and suddenly is available, I'm always willing to have a look at them because they might change the field again. Anyhow, so let's look at the efficiency factor. So what can I do? There's a number of games I can play. So as I said already, the key thing that's going to determine the amount of power I can get is this heating factor. SAR, specific absorption ratio, is basically how much of that electronic power that you basically put electromagnetic power is turned into heat. And I remember the 1 degree Celsius. Now it turns out SAR is only a function of the electrical field, not of the magnetic field. So if I can minimize the electric field, I can do some interesting things. I actually can transmit at higher power levels. The way you can do that, one way to optimize this, if I would use at the external side a simple loop antenna, and you plot the electromagnetic waveforms, you can see, or electrical waveforms, you can see that around the feeding part, the feed point is where the electrical field gets maximized. And much higher than the other side of the loop antenna. So if I now redesign this antenna to become, let's say, a segmented antenna, which you have inductance, capacitance, suddenly you spread the electrical field around, it goes down in global, and suddenly I can start actually transmitting at a higher power level. It saves me about 47% at 500 megahertz transmission. That's nice. Something by just antenna design, I already can get a little bit more power to my node delivered. You obviously can also play with the antenna sizes. The frequencies, what is the optimum frequency, what's the optimum antenna size from the external side. And by doing so, we figured out, for instance, by optimization, you say, well, around 400 megahertz and about 1.5 centimeters on the outside is where I get my optimal power number. And you simulate the whole darn thing and you figure it out, but ultimately you have to check if it's real. So you do a bunch of experiments with animals and you put the measured channel, and indeed it turns true that you actually can do these things very nicely. You can model them very nicely, so we can move forward to the next step of the design process. Now, so this is cool. So you can basically optimize the amount of power we can deliver, but it is not as fun if you basically provide a bunch of power, but you cannot use it effectively. So some way, somehow, I have to take that RF power and turn it to real DC power I can use. And that's a challenge as well. You need somewhere an RF to DC type of component. Now, these are always based on diodes. Right? Every time I basically go from, you basically rectify using a diode. Now, what you know about diodes is that typically you have about 0.5 volt. You need a minimum of 0.5 volt to hit kind of the diode in the extreme nonlinearity. If you don't get there, you don't really get a very nonlinear behavior, you don't get very good efficiency. The problem is, if I take my small antenna, and I look at basically the waveforms I'm getting around, what I'm seeing is that I get about 0.1 volt signal instead of 0.5, and the efficiency of my rectifier goes down substantially. Most of the power I transmit at it, I cannot rectify. What I really would like to see is a larger signal, but I don't have it. So how do you deal with that? Well, again, you play some tricks. Again, that's something which is very welcome. So and that's the way we basically operate those nodes. Okay, so here's kind of a proof of concept. This is an example of a system we built. Here's the outside antenna, one of those segmented antennas. This is the internal antenna. It's a millimeter square antenna built on a micro PCB, 2 loops, basically in copper. And then you have a chip of the same size, which is basically flipped on top of it. Complete system, so you can see the really tiny size. And this consists of an RF to DC converter, references, and all these kind of things, and basically ultimately generates you to some DC voltage. And what we see is that depending on what type of spec standards you use, so sometimes it's better to use the IEEE standards, gives you a little bit more power than the FCCs. But anyhow, between 8 microwatt to 26 microwatt of power. And you see the node here sitting on the cortex of, this is a suckling pig. A dead one, by the way. Don't worry about it. Anyhow, so, okay, now we're basically around 10 microwatt of power. Now, with that power, I have to do all the rest of the electronics. So what can we do? So the most important part is that most of the power is going to go to the signal acquisition. You have a signal that is really tiny, noisy, offset, all those kind of things, and I want to turn it into something decent. So that's really what you want to basically focusing on. This analog front end takes a bunch of power. Now, if you look at the traditional way, so remember, all of those things are not very fast. We're talking about the pulses are 10 kilohertz bandwidth. The low frequency is about 300 hertz bandwidth. And you have your offset type thing. So it's slow frequency processing. But the real challenge is getting rid of that large offset. If I have a large offset there, I'm going to swamp my whole system. I'm going to be in trouble. So the traditional way of dealing with that offset is to do AC coupling. You put a big capacitor before you go in. But the problem is with that capacitor having basically something that filters the offset but doesn't get rid of the low frequency contents is a problem. So you end up with a huge capacitor which takes virtually all of the area of your chip, basically fights your miniaturization approach. So how to get around that? Well, the answer is, hey, we have darn good digital transistors. Digital basically said, well, if you basically scale technology, you go to the scale technology, gives you plenty of nice, small digital transistors. So rather than trying to do a lot of stuff in analog, what you do is you go away, try to get away with a kind of crappy, or not a very good analog front. It's still a good one, but it's not as high. Fairly low resolution, a couple of amplification stages, and then you use a digital feedback loop with A to D converters to basically cancel the offset and separate the low frequency and the high frequency contents. So use of digital type of transistors to solve this. And if you do so, you end up with a whole front end, which is about 100 of a square millimeter for this whole acquisition channel. It takes about 5 microwatt, runs off a 0.5 volt supply. For a mixed signal, that's not bad. Definitely for very high, high SNR type of characteristics, that's darn good. So avoid large capacitor by DC coupling and filtering in the digital domain is really the whole idea. And no precision analog components. Again, you can build this thing. This is an implementation. It's really tiny, so I can put a whole bunch of them on a single die. I can have multiple channels. And this is this amplifier implanted in a RAD, and you can see the waveforms as you can see them come in. This is your input waveform. This is our spike waveform. You can see the spike forming. This is a low frequency component that's superimposed on top of it. Okay, so about 100 of a square millimeter, a couple of microwatt, 4 microwatt approximately is what we believe we can do. Now what's next? Well, obviously I can take all this complete waveform and now transmit it out. But that's going to put some pressure on my RF. I'm going to have a communication link that can take this complete waveform. Now, neuroscientists like these waveforms. They like to see everything. Neurosurgeons or BMI people say, I don't care. What I really care about is when do you spike? That's the only information they want to see. So can I extract that information up front and compress the waveform before I transmit it out? Again, how much power is going to take you to do this kind of advanced signal processing? This is kind of things you need to do. This is spike extraction. You have a bunch of spikes. Actually, a single electrode might see multiple neurons in its neighborhood. So you have to be able to differentiate between those. So you first time normalize it. You put them on top of each other. You follow some trajectories, and then you can recognize different spikes. And you can put the timing on them, and you're basically done. Now, that's taking a lot of power, right? Well, no. Actually, we can take this whole thing and turn it into a little digital processor and kind of push again extremely hard on the supply voltage. Again, energy is all about supply. Turns out we can actually run a processor like this at about 0.25 volt. Now, you worry about when you go to these very low voltage levels that you're going to be dominated by leakage and variability and all those kind of things. So the way to get around that is say, well, we're not going to do this kind of synchronous type thing. We go completely self-timed. By doing completely self-timed is a structure like this. You basically automatically adjust to process variations. You basically put every gate, when you don't use it, automatically in low leakage mode. So it has automatic power management built into it. So it basically helps us to manage the overall leakage power, which is still the dominant source. But the bottom line is we can save about 75% power over a traditional digital synchronous implementation. So about a quarter of a microwatt per channel at 0.25 volt is what we think is possible. And again, it takes only about 0.03 of a millimeter square in CMOS. Okay, so we have our data. We can compress it. We have to transmit it out. Again, you might worry about how do you transmit it out. The radios take a lot of power. But here we can ride shotgun on the fact that we already have that power delivery mechanism. We have already that RF link, so we can do an RFID type strategy. And remember the pulsing? So the way you run this thing is occasionally you pulse the power. Right, there you go. But in between, you keep a waveform going at a lower level of amplitude. And I'm going to use this waveform to reflect data backwards. Just by modulating the antenna, by using an antenna modulating switch, I can go back and forth. And actually, in this case, we came up with an interesting scheme that uses a combination of RFID strategies with ultra-wideband. We modulated very narrow pulses. So the waveform we're getting back, we send a very narrow frequency waveform in, we basically modulate it, and it comes back as an ultra-wideband or wideband type signal. So all doing this thing, you can see this is the thing operational. You get about 2 megabits per second, 300 femtojoule per bit for a radio that's about 100 of a square millimeter. So bottom line is, using all the strategies, we now start seeing that all the components are definitely possible. We have all the pieces. Now start to dream about what type of systems can you build to really form effective long-term BMIs. So this is something we're playing around with today. I call it neural dust. The idea of having a bunch of little neural sensing nodes that are freely embedded in the neocortex. Basically, they're floating around so that they have a minimum impact. Each of them has a bunch of electrodes, as you can see. Here you have the electrodes sitting on the pin, a bunch of amplifiers, and a radio on the top. Or it could be tethered, one of the two. You can have one of the flexible tethers that goes to a node. On top of that, you put those interrogators. Interrogators are basically interrogating those floating nodes, getting the data, and then again wirelessly transmitted to the outside world. And again, 4 or 5 years ago, this looked like science fiction, but really pushing hard on miniaturization and power, we believe now that these things are within the realm of the possible. Now, this is the one approach, but obviously it's always good to keep on dreaming and think about other solutions as well. And one example here, for instance, is the Econ approach. Here's the Econ strategy I already showed you before. Really nice, but the problem is this resolution of 0.5 centimeters. Now, if I look at organic type of electronics, I see actually that today we should be able to do things a lot better than this. Actually, using semiconductor lithography, why not start thinking about arrays of electrodes that are far denser? I can use lithography to basically put electrodes on spacing of about 100, 200 microns and basically get much higher resolution without needing those specific needles that go into the cortex. We call this the micro-ECOG, and instead of having 0.5 centimeters, we think we can go below half a millimeter in spacing. Again, what this requires is that you have a whole bunch of amplifiers now that sit there, collect the data, multiplex it, get power for it, and then transmit it out. And that's kind of the vision of another system we're building, which indeed has an array of electrodes printed on parallel. We print the antenna around it in this case, because now we have a big array, we can just nicely put an antenna there, and you have a little chip basically that acts as the interface and which has a whole array of amplifiers sitting in parallel with each other. And again, think about this couple of microwatts per amplifier. You put 64 of them or 100 of them, you get about 500 microwatt. But since the fact that now I have a much bigger antenna, I can get more power in here, I should be able to sustain that. One of our dreams is that potentially we can go to 1,000 channels. But this is going to require some advanced signal processing. So the ultimate picture is the one I show here. This kind of picture we've drawn with a couple of my colleagues is where you have a complete system that basically can operate at multiple levels of granularity, going from floating needles that either are connected using tethers or wirelessly to those macro Econ arrays, and then talking to the external world using a secondary wireless link. So, well, that's just one idea. There's many other ideas you can think about. So if you heard Ming's talk before, there's another field which is called optogenetics. Optogenetics allows you to basically put signal in there using optical strategies of stimulation. So a combination of this with optogenetic approaches might be very interesting as well. So reflections. So I think brain-machine interface to me are the ultimate in immersive technologies. It cannot get a lot closer than that. Potential is huge. Initially it's going to be societal impact, but ultimately it's going to lead to human advancement. It requires really ultra-low power strategies. We're talking ultra-low power, is anything microwatt level is really what we're thinking about. And it requires combination of technology, devices with circuits, systems, brings everything together. You really have to think through the stack to basically get to those power levels. Key thing is, don't forget what you're trying to build. It's always nice to play around with the device, but what are the type of functions we build? It's really the system. And what is the information that's useful? Think also about the fact that the brain plays a role in this whole system as well. Brain is an amazing plastic device. Getting integrated in the loop is really crucial. And finally, it's a collaborative effort. It really requires many people working together at various fields of engineering. That's why you have so many names that I have to thank for this presentation. Thank you. Yes.
So, saw a lot of how to pick up the signal from the brain.
Mm-hmm.
Oh, sorry. But can you talk a little bit about your thoughts about how to do the feedback? So how do you put a signal back into the brain using one of these things?
So it really depends what you're trying to do and what type of functions you try to accomplish. Obviously, if you look at prosthetics, it's purely an outputting. You image, and your prosthetic, you drive a device. But obviously, there's other applications.
Do you need, like, spatial awareness? Like, you want to be able to close your eyes and touch your nose kind of thing?
Possibly, if you, but again, the question is how do you train, right? It's a trained system. So the initial training has to be done using feedback. So you basically either have tactiles or you have something, you feedback. But after a while, you have rewired your neural circuits. And at that point in time, actually, you should be able to move the arm with your eyes closed. So stimulation, though, is useful as well. Neurostimulation can do certain things. It helps you to rewire some of these neural circuits faster. If I basically have a way of injecting signals to particular neurons, I can actually wire them quicker. And there's a bunch of experiments have shown that even with mice and rats, you actually can rewire those things in a very short period of time. It's a challenge, though, because the problem is stimulation typically is done through currents. You inject a little current next to that neuron. Now, currents, I mean, you look at my power budget, I have not much room left to basically inject currents. But the good news is actually you don't really need that much. So it's something that's interesting. But that's also why people look at optogenetics, using optical signals to actually do stimulation. Now, there's other fields, like, for instance, cochlear implants and artificial retina are the opposite. Right? There you have your sensors that are broken or disconnected. And what you do is replace the sensors by artificial sensors like cameras or microphones. Obviously, they're driven by stimulation. And there they typically use either, most of the time they use current or voltages to do so. But in certain cases, people are also thinking about using chemical interfaces. Why not use some type of ionic device, ionic type of thing like potassium to basically do stimulation as well. So there's a bunch of options, but stimulation is, from my perspective, harder than imaging. So let's start with imaging. Yes.
You mentioned that the rectifiers you're using for your RFID needed like a 1 volt.
Half a volt.
Turn on?
Half a volt.
There are diodes with much smaller, with
True.
zero bias.
True. The key question, though, do you get them in a standard CMOS process?
No.
Exactly right. So that's everything we've shown here. There's no special process options. These are just standard run-of-the-mill 65 nanometer processes. But you're right.
Just got them a few years.
Yeah, no. Hey, as I said, you come up with nice devices, I'm going to grab them when they become available. And if it improves the efficiency, if it gives me a little bit more power, hey, it's well taken.
Is the 1 degree limit a real limit in the sense that, that comes from all sorts of funny non-physics stuff, right?
That's right.
Where like, if somebody really needs this and you prove it in the lab at a little bit higher, let's say 2-3 times higher.
Mm-hmm.
I imagine if I can't operate an arm, I'll sign something saying go ahead, make it 2 degrees, make it 3 degrees.
Yeah.
So is it a real thing?
It's a very good question. I've been asking this many people, and nobody knows. It says somebody at some point in time said, what's a good number? Well, 1 degree seems like a good number, so that's what we're going to stick to. And all the standards, like your cell phone against your head, is all based on that 1 degree type of number. So, but it's at the same time, it's good to take a spec, right? I can transmit at 100 times level. You're going to basically run right away into problems if you want to start deploying those things. So sticking to the standards seems to be like a good idea, at least from this health perspective.
Right. It's making you go for a very hard target, but at the end of the day, you may have an easier time when you actually go to implement or whatever.
That's right. And you're right. And your argument was totally correct. Again, you ask any neurosurgeon, says, who would be crazy enough to basically let their skull be lifted off and all kind of stuff happen? He said, when people are desperate, when they really have serious type of these, they're willing to take anything. And they really are willing to take risks. So you're right. For the early deployers, the 2 degree type thing might not matter if it basically gives some thing back in life. But later on, obviously, you want to be...
Eventually you have to...
Exactly right. Mm-hmm.
Take risks until something goes wrong and they sue you.
Yeah, no, they sign papers.
Sign again and try to beat it.
Mm-hmm, mm-hmm.
It's only if it's someone famous, like a politician.
All right.
Any other questions? Yes.
I'm just curious, you mentioned neural dust. It reminds me of Chris Feaster's.
That's right.
So there's a Chris Feaster test. I don't know if you've taken it. Chris hasn't taken the test. Start over. You mentioned smart dust and neural dust, which reminds me of Chris Feaster's smart dust.
Sure.
And there's a Chris Feaster test, which I don't know that Chris Feaster's taken, but the impact of actually eating one of these devices or the long-term effects of having the device in the body. You have to go through a lot of testing or something, right?
Right.
Or encapsulation.
Yeah. No, absolutely. Packaging is important. But like, for instance, I showed the ECOC type stuff. ECOCs are Parylene is a material that's been used forever for implants. We use, for instance, the printing material we're using is platinum. Platinum is used quite regularly for a lot of the implantable devices. Silicon in itself is not harmful. I think most of the things that we're talking about, actually, I wouldn't mind taking one of those millimeter cube notes and digest it. That's an easy one, because people have done much bigger things. They have these large pills that you can swallow, and that basically travel to your body and do imaging, while they're traveling to the body, basically taking images and so on and so forth. This is a lot smaller, and a lot less lethal, I think, than these big pills that are out there.
All right, that's it. Thanks, Jan.
Welcome.